Well, over the last 2 weeks, you have studied working of carbon dioxide laser, which is also the very first molecular gas laser to be developed, when an Indian American scientist, C.K. Patel, operated it for the first time at Bell Telephones Laboratory in USA in the year 1963. This laser has also the distinction of being the very first laser to be used as a light scalpel for bloodless surgeries. As you know now, carbon dioxide laser is one of the most important lasers and is now indispensable for both industrial and medical applications. It is essential to understand some aspects of molecular spectroscopy to appreciate the working of a molecular gas laser. And therefore, for this course of carbon dioxide laser, a few weeks were spent in the beginning on molecular spectroscopy. And having now acquired an elementary knowledge of molecular spectroscopy, you are now in a position to understand working of two different varieties of lasers. They are chemical lasers and gas dynamic lasers. Although light emitting species for both these lasers, that is chemical lasers and gas dynamic lasers, are molecules, yet they cannot be represented, they cannot be categorized as molecular gas lasers. They cannot be categorized as molecular gas lasers because the way to pump this laser, that means the methodology to create population inversion in these lasers, differs significantly from the way a molecular gas laser is pumped, like the carbon dioxide laser. Today, we begin to take a look at the working of chemical lasers, and subsequently this will be followed by the working of gas dynamic lasers. So all right, let us begin first with chemical lasers. See, whenever we think of chemical lasers, the first thing that crosses our mind is the Star Wars program. You see, in 1980s and early 1990s, when Cold War was at its peak between America and Russia, and when Ronald Reagan was America's president, then America initiated an ambitious program that was aimed at developing an air defense system by placing lasers at strategically located orbits to dispel the threat of a nuclear attack. This ambitious plan relied heavily on high-power airborne lasers with the capability of striking any nuclear warhead that would have been fired from Russian or any other enemy country's soil located anywhere in the globe. The idea was basically to destroy the missile carrying the nuclear warhead in its boost phase, just after the launch, in the sky of the country of its origin itself. For this, a chemical laser that does not require a significant amount of electrical energy for its operation and is capable of delivering light beam of colossal intensity emerged as the most suitable for deployment in an Earth orbit. In this context, it is of worth noting here is that President Reagan, a vocal supporter of the Star Wars program, advocated that lasers in space would be a tool to rid the world of nuclear weapons and did not rule out the possibility of eventually sharing the knowledge that would be acquired through this endeavor with even Russia. However, owing to cessation of Cold War in early 1990s, this scheme was eventually shelved. Of course, after some initial test experiments with mixed success. And from these experiments, it was, however, established that the potential of a chemical laser that does not require usually electricity or appreciable quantity of electrical energy for its operation and is capable of delivering a light beam of colossal intensity, which is essential for achieving success in any military applications. You'll have to deliver huge amount of energy within a short time to the target. And this chemical laser was capable to achieve this. So they actually emerged as the most suitable for deployment in the Earth orbit. And it is not surprising that the major thrust of the development of chemical lasers actually stemmed from their potential to defend against both short and long-range missiles that would carry the nuclear warhead. And the most significant advantage is that during the travel time of this pulse light beam containing huge amount of energy, as it travels to the missile, then during the time of its travel, the missile would appear to be almost at rest, however fast it moves. Because light travels, as you know, in extraordinarily high speed. And thus, the end result would be a precision strike. You do not have to consider the velocity with which the missile travels. So it would be a precision strike. That is the advantage of using light as compared to a conventional weapon. All right, so let us begin with this introduction with our understanding on the working of a chemical. As we know, it is, of course, a molecular gas laser, although it cannot be categorized this group, and it operates in the infrared region. You already know it because having studied the operation of carbon dioxide laser. But let me just delve a little to enlighten you a little more on why a chemical laser would usually operate in the infrared region of the electromagnetic spectrum. You know that just like an atom, a molecule also has its electronic energy levels, because molecules have energy, electrons, and therefore it does possess electronic energy, excited energy, ground electronic energy level, then the excited electronic energy levels, just like an atom as we know from Bohr's theory. However, the constituent atoms of a molecule can also vibrate, and while they vibrate, they also can rotate. And just like the electron's energy is quantized, the vibrational energy and the rotational energy are also quantized. So let us take a little deeper look. Suppose this is the ground electronic state of the molecule. And this is, suppose, the first electronic excited state of the molecule. Now the molecule is also vibrating. The atoms constituting a molecule are vibrating. What is the vibrational energy? The vibrational energy is also quantized. And the energy that is required to excite a quantum of vibration is much less than the energy that is required. So this energy would be required to excite the molecule electronically from, say, ground state to its first excited state. This is the energy that will be required to cause an electronic excitation, which we call delta E, electronic. The vibrational excited state, which are also quantized, the spacing between this vibrational energy, vibrational excited states are much too less compared to this spacing, compared to this spacing, and the separation between two adjacent vibrational states are same. So that means if I draw in this scale very qualitatively, the vibrational excited state can be denoted like this. They are equispaced, and so this is the V equal to 0 state. This is the first vibrational excited state. This is second. This is third. This is fourth, and so on. And all these vibrational states also have its own rotational manifold, because as you know, the molecule, when it vibrates, the atoms can also rotate, and the rotational energy is even smaller than the vibrational energy. So for each vibrational level, as you know, there will be many rotational levels. And I'm not going into detail because you know this already. So suppose, let us consider a transition between, say, this state to this state. This energy difference is, we call it delta E V. So the transition from this to this will emit light of frequency, say nu, h nu we call it V. This is vibrational transition, which will be equal to the spacing between these two levels, energy gap, energy spacing, delta E into V. And therefore the frequency will be equal to delta EV by H. And for electronic transition, let us assume from the ground electronic state to first electronic excited state. If there is a transition from this state to this state, then the light that will be emitted, the frequency of that will be, we call it nu electron, will be equal to delta E divided by H. As delta E is much more than delta E, therefore frequency of this electronic, frequency of the photon arising out of this electronic transition will be much more than the frequency of the light arising out of this vibrational transition. Or in other words, if we express it in wavelength, the wavelength would be the wavelength of vibrational transition will be much more than wavelength of electronic transition. Now, in the electromagnetic spectrum, suppose this is my visible region, this is the ultraviolet, this is vacuum ultraviolet, and goes on. And this side is the infrared region of the electromagnetic spectrum. Now this electronic transitions, atomic transitions, usually emit light that spans across this visible region, the wavelength. So the wavelength increases in this direction, spans the visible region. And this is for electrons, the outermost electrons. And as you know, when we studied the ion lasers, if we involve the electrons which are deeper down and closer to the nucleus, then the transition arising out from the electronic energy levels of those transitions, inert electrons, can give rise to emission of light that goes into the ultraviolet and into the vacuum ultraviolet region of electromagnetic spectrum. However, the transition which arises out of this light which arises out of the transitions between these vibrationally excited energy states emits light that lies in this infrared region of the electromagnetic spectrum. So then, a molecular gas laser usually would emit light at infrared. So, fine. Now, unlike a conventional laser, which is usually powered by, as you know, by powered optically, you now know it very well, or electrically. As you know, a conventional laser is usually pumped optically or electrically. And to refresh your memory, solid state lasers with the exception of course, semiconductor laser, which we will study later, and liquid laser. They are usually pumped optically, and while the gas lasers are usually pumped electrically. These chemical lasers are powered by chemical reaction. The energy that is stored chemically in the reactant species can actually be utilized to achieve pumping or create population inversion. And the possibility of a chemical reaction pumped laser was first conceptualized by a Germany-born Hungarian-Canadian chemist John Charles Polanyi. In 1961, soon after the invention of laser in 1960, he realized the prospect of the excess energy liberated in a chemical reaction. As you know, in a chemical reaction, often energy is liberated. He first realized the prospect of using this energy to vibrationally excite the molecule formed in the process. So basically, what he thought is that, suppose let us consider two species, A and B, which could be either atom or molecule. They react and form, suppose, a molecule which is AB. And this molecule is formed in a vibrationally excited state. So now you know that this molecule has, let us consider this is the ground electronic state of this molecule AB. So then there will be vibrationally excited. This is also V equal to 0, the ground vibrational state. This is the first vibrational excited state, V equal to 1, this is V equal to 2, this is V equal to 3, and so on. And the molecule that will be formed, this AB molecule, it will be formed in a vibrationally excited state. And the probability of its being formed at different vibrational excited states are different. It basically is a result of the chemical kinetics of these different levels and the spectroscopic rule. Let us not go into any deeper. But because the probability of formation of this molecule in different vibrational states is different, therefore there is a possibility that some state, like say 2, will have a population, these molecules that has been formed in the state 2, and the number of molecules that has been formed in the state 1, vibrationally excited state 1, is less than N2. That means N2 is greater than N1. Meaning you have created a population inverted condition between these two vibrationally excited states. And this has happened just as a result of the energy that was liberated in this chemical reaction, and this energy has been transferred as the vibrational excitation energy of the molecule in such a way that you have created a population inversion. Now, if you place this population outer medium inside a cavity, then you will be able to amplify light between this transition, which has resulted in population inversion. The pioneering work, it may be also interest to note that the pioneering work on chemical reaction dynamics and the kinetics of these levels eventually fetched Polanyi the 1986 Chemistry Nobel Prize. American scientists Jeremy V. Caspar and George C. Pimentel operated the first ever chemical laser at the University of California, Berkeley, in the United States of America in 1965. Almost 4 years after the possibility of a chemical laser was conceptualized in 1961 by Polanyi. And the very first laser that these scientists at University of Berkeley, California operated was by initiating a chemical reaction between hydrogen and chlorine with a flashlight. So what they basically did, hydrogen gas and chlorine gas, the hydrogen molecule and chlorine molecule, in presence of light that they derived from a flash lamp. You know now what is a flash lamp. This actually triggered the chemical reaction between them, and it resulted in the formation of hydrogen chloride molecule in the excited state. Now, the same reason as I just explained, that this hydrogen chloride molecule will have, we are considering its ground electronic state, many vibrationally excited levels, and then they will be formed at different rate at different levels. That will result in achieving population inversion and in turn amplification light and lasing, giving out coherent light at the corresponding wavelength between which the lasing transition takes place. So this automatically established population inversion condition prerequisite for lasing. So subsequently, after they operated the first chemical laser with by making use of hydrogen chloride molecule, the operation of a variety of chemical lasers has been demonstrated, of which the most important lasers, or the lasers that have gained a lot of popularity and attention, are hydrogen fluoride and deuterium fluoride, in particular from their importance from the military application point of view. So they attracted a lot of attention of military developments. However, there are, in this regard, I would like to just spend a few minutes. You see, HF laser emits light at wavelength because there are vibrational rotational transitions from many levels are possible. Therefore, this laser will, like carbon dioxide laser, can also emit at a number of wavelengths, and they actually span over 2.6 micrometer to 3 micron wavelength. So the light that would be emitted by HF laser usually lies in this range of the electromagnetic spectrum, 2.6 micron to 3 micron wavelength. And this light is very efficiently absorbed by atmosphere. And therefore, the beam of light emitted by such a laser would not travel without any absorption through the atmosphere. This challenge provides some challenge as far as the military application is concerned, because the light would not reach the target with its full energy. If this hydrogen is replaced by the heavier isotope of hydrogen, that is deuterium, then the emission of the laser spans, that is the deuterium fluoride laser, from 3.6 micron to 4 micron. At this wavelength, air has very good transmission. Therefore, as far as transmission is concerned, this laser scores better than hydrogen fluoride. However, as far as military application is concerned, this still faces some challenge. That is because the wavelength being longer than this, the emission of hydrogen fluoride laser, the focusability of this DF laser's emission is not as good as of hydrogen fluoride laser, simply because the wavelength is more. It undergoes more diffraction. You already know this. And therefore, this further provides challenge to military application. I think I would end here today, and let me just mention that in this context, there comes another laser, which is coil laser, which actually is ideal as far as military application is concerned. This we'll study in the next class.